Alright, so happy studying. Today we're going to be talking about friction. So what is friction? Well, if I had my marker, right, and I slid it across the table, by Newton's first law, if I slid it at some velocity and let go, it will go forever in that direction with that velocity. But that's not the case, right? If I slide my marker, the marker eventually comes to a stop. It slows down and it stops. Okay, but Newton's first? No, because there has to be some change in velocity that's happening, right? There has to be some change in velocity that's reducing the velocity. So my acceleration has to be this way. Well, by Newton's second law, we know F is equal to ma. The mass of the marker isn't changing throughout this entire trip, so that means that my acceleration, if it's decreasing, my force has to be, or my acceleration is negative, right? It's in the opposite direction. I have some force that's acting in this direction. So what does that mean? That means I have some force here, a resistive force that's resisting my motion. And I'm going to call this force friction. I can denote it with a small f, or I can denote it as F of F. What makes friction? Well, if you look at this marker, it looks really smooth. But in reality, there's tiny microscopic bumps on it, so I can draw it like this for emphasis. And the chair itself also has microscopic bumps on it, like this. And these interlock, right? If I try to push things that look like this, like two interlocking pieces together, it's almost impossible, right? I have to apply a lot of force to overcome it. I have to apply a lot of force, and then once I apply enough force, it's gonna start moving, and it's gonna do bump, 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 as these interlocking pieces move and slide past each other. It takes force to overcome all of those bumps. So there's two things that I said are very important. One, it requires me to first apply a force in order to get these things moving, and then while they're moving, there's still a friction resisting it, because all these bumps are pushing the object in this direction. It's as if it's resisting my motion. So let me give another example. If I have my hand and I'm on this whiteboard, right? I'm going to push, I'm going to push, and then finally it can start to move. I'm going to push, 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 and then it starts to move. I have to first apply a force before my hand starts moving. If you have a stapler with a grip on the bottom, or maybe your laptop has those rubber grips, try sliding it across the table. You have to first apply a certain amount of force before your laptop is going to start sliding. Now that is important. When the object is not sliding, what is the net force on the object? Well, the net force has to be zero. The velocity is zero. The change in velocity is also zero. So I have no force on the object. So my applied force, right, and my frictional force are going to be the same, right? This is the my frictional force and my applied force. These are the same exact thing because they have to add to zero. They have the same magnitudes, even though their directions are opposite. And that's something also important to keep in mind. The direction, friction always opposes the direction of motion. So if I'm moving my marker this way, it has velocity this way, friction is going to be in this direction. And if I move it like this way, friction is in this direction. Alright. But then, after a certain point, the object can start moving. So even though I'm increasing my applied force, my frictional force is not increasing proportionally enough to counteract all that applied force. In fact, this is how the friction looks after that. So what I'm going to do is I'm going to break up this diagram into two parts. This is what I call static friction. Why is it called static friction? Well, the object is static. The object is not moving. And this is the friction that's applied on the object when it's static. And this thing here is called the kinetic friction. Right? As I'm moving my object, eventually it starts to move, but there's still some frictional force being applied to it. The friction while moving kinetic means motion. And let's dissect this graph. So right here we know that these two things are equal, but here the kinetic friction actually drops and levels off to some certain constant level. And this kinetic friction is specific for whatever objects we're using. Like if I was sliding ice on an ice rink, that would have a lot lower friction than if I was sliding like my laptop with its rubber grip on another laptop with a rubber grip. It would be really hard to move. Alright, so how can we calculate these two values? Well, the first thing I can find is what is the maximum static friction of the object. Well, F of S, the maximum static friction on the object, which I'm only going to denote F of S, actually I'll do max, is equal to the coefficient of static friction, and this coefficient is denoted by this Greek letter mu, the coefficient of static friction, multiplied by my normal force? What? Alright, if you remember, normal force is the force an object, the surface exerts on the object. So let's first analyze what all of these things mean. Coefficient of static friction. It's going to be higher if your thing is more resistive to motion. So like my laptop with rubber grips is going to have a huge coefficient of static friction because it's super hard to slide across things. It likes to resist my motion. But an ice cube is super easy to slide across things, so it has a very small one. Does it make sense that my maximum static friction force is proportional to my coefficient of friction? Yes, because if I have a high coefficient of friction, it's going to oppose my motion a lot. Low coefficient, it's going to oppose my motion a little bit. Now what about this normal force thing? Well, imagine that I have my objects again, right? And I push them into each other, right? So these things are interlocked. They're very interlocked. It's going to take a lot of force in order to get them uninterlocked and start sliding across each other. On the other hand, right, if the force, the surface, which is like, I'll say is the bottom one, right, applies on the object is very low, so they're not as interlocked, it's much easier to get them slide past these tiny, tiny ridges. It's a lot easier to go whoosh, because there's less forces that are applied onto each other. So does it make sense that if the surface is applying more force on it, right, these things are more interlocked, that we have more resistance? Yes. Does it make sense if we have less? There's less resistance? Yes. Alright, so what about this kinetic friction? Well, actually, kinetic friction is, we're just going to say it's a constant because it's a constant from here on out, is equal to this kinetic coefficient of friction multiplied by F of n. Very similar formula, right? And something that's very important to note is that this mu of s is always going to be greater than this kinetic coefficient of friction. Why is that? Well, that's because this point here is higher than this point here, right? We're multiplying both of these things by f of n to find f of whatever, either f of s or f of k, right? We're multiplying by the same thing, but this thing is higher than this thing, right? That means this coefficient has to be higher than this. Yeah. So now that we know this, let's try to come up with let's try to solve a friction-related problem. So here is the problem. Let's say that we have an inclined plane, right? We know the angle of repose, this angle of the inclined plane is theta. We know that the object is on the brink of slipping. So in our friction versus applied force diagram, it's right here, but it's not moving. It's on the brink, but it's not moving. And we also know that the mass of the object. Let's say that this is m. Can we find the coefficient of static friction? Well, let's try to attempt that. First things first, we draw a free body diagram, right? We have gravity pulling it this way. Its weight is going to be Fw, which is mg. And for now, actually we'll wait off a little bit. So then we also have its normal force, the force the surface applies onto the object, right? So what direction is the surface applying on the object? It's kind of like this at an angle, like this, right? And the angle is perpendicular to the surface. The normal force is always perpendicular to the surface. And then we have a frictional force, right? If the object was allowed to slide, which way would it slide? Well, it would slide this way, right? Gravity, part of gravity is pulling it this way, in this direction, down the slope, right? There's a component that's going this way. That means friction is going to be here because it has to resist that motion. So here is F. Here's Fn, right? And these two things are perpendicular. Friction is along the surface. Friction is always going to be along the surface, while normal force is always going to be perpendicular to the surface. All right. Now, since these are perpendicular, I'm actually defining this as my positive x direction, and this is my positive y direction. And the reason I can do that is because all that matters for x and y is that they're perpendicular to each other, right? X and y are just coordinate systems. It doesn't matter that they're horizontal or vertical. No, we can define them whatever. And it'll make it a lot easier to work with. So, this object is not moving. That means its net force is 0. So its net force in the vertical direction and the net force, or in the y direction, and the net force in the x direction have to be equal. Alright, so what are its forces in the y direction? F of y net is equal, well, we have the normal force, F of n, and what else do we have? We have this component of the weight, which I'm going to call F of y, F of wy. We also have, in the x direction, what forces do we have? We have our frictional force, right, F, and it's static because it's not moving, plus this here, which is F of w in the x direction. Alright, so interesting. We have these equations. Are there any other relationships that we can find? Like, can we relate this to F of w itself? Actually, yeah, we can. If we draw this onto this diagram, right, here is gravity. Well, gravity is going to form a right angle with this table, right? Imagine this inclined plane was on a table or on the ground. Gravity is going to form a right angle here. That means this angle is theta, or 90 degrees minus theta, right? So this is 90 minus theta. What does that mean? Well, here, right, we have the component that's along, here we have the gravitational component, right, F of wy, that is along the direction of the normal force, that is perpendicular to the surface, right? So that means that this makes, this is perpendicular to here, so this is also 90 degrees. Alright, so that's 90 degrees, and here's Fwx. This is 90 degrees. What do we know from here? We can actually discern that this thing is theta degrees. Well, why is that theta degrees? Well, if you know, right, this thing is perpendicular here, and then this angle plus this angle is equal to this angle, the angle between Fwy and the surface, right? This angle plus this angle is equal to this angle, which is 90 degrees. 90 minus theta plus theta is equal to 90 degrees. We use some basic angle tracing to find this is theta degrees. Well, if this is theta, what does that make Fwy in relation to Fw? Right? Well, the cosine of theta is equal to Fwy over Fw, right? Adjacent over hypotenuse. So that means Fw cosine theta is equal to Fwy. Similarly, we can find that Fw sine theta is actually our Fwx. So let's plug in those values. Here and here, these values will replace them here. Fn plus Fw cosine theta, and here plus Fw sine theta. Alright, well, what else do we know about these forces? Well, we said the net forces are 0, so let's replace this side with zeros. Because we already know these are the sum of our y and x net forces. So here's 0, here's 0. I should write newtons. It's good practice to write newtons. Yeah, you know what, I'll do it. Okay, here are newtons. Alright, well, now let's find what Fw is in relationship to f of n. Fw, right, is equal, let's move Fn on this side, negative Fn, and we divide both sides by cosine theta over cosine theta. Alright, that's pretty cool. So let's plug in this value into here, and what do we get? Well, we get 0 newtons is equal to f of s plus negative Fn, right, negative Fn over cosine theta multiplied by sine theta. We know sine theta over cosine theta is tan theta, so this is equal to f of s minus f of n tan theta. Alright, so now let's write this equation at the top. 0 newtons is equal to whatever we have found, right? So we have 0 newtons on one side is equal to f of s minus f of n cosine theta. Well, we know that f of s, right, is equal to mu s f of n. So let's just plug that in here and move this onto the side. So we get on the left side we get fn cosine theta, and on the right side we have f of s, which is equal to mu s f of n. Oh, I messed up. This is tan. This is a tan. Oopsies. I am okay. Alright. And now, what we can do is we can divide both sides by f of n, right? We have f of n here, and we get mu s is equal to tan theta. That is a beautiful discovery. We just found that if this object is on the brink of moving, right, the coefficient of static friction is going to be tan of theta. And we can find, yeah, is equal to tan of theta. So experimentally, how can we determine the coefficient of static friction? Well, let's say we have an inclined plane. Let's measure this angle of theta, right? And then what we do is we have this mass here. We don't know what the mass is, or we have a box here. And let's just keep adding masses, like let's say we added like little balls that are masses, until the object slid. Well, then we take away one of those balls, and then we can say that the object is on the brink of sliding, because as soon as we put in the next ball, that tiny bit of mass, the object is going to start sliding. We can be more precise about our measurement by adding smaller and smaller balls as it's about to fall, and using really, really tiny masses to figure out exactly what mass is going to take before it starts to slide. Then we can find the coefficient of static friction between these two surfaces. So let's write down all the things that we've learned in this video to summarize. All the things you can put on your equation sheet for the physics C test. Well, first one we've learned is that F of S, right, is equal to mu S F of N. What is that? F of S is the maximum static friction, right, on the peak of the curve. So here's our curve again. It's right here. We also know that F of K is equal to mu K times F of N. Mu K is like right here, or F of K is like right here. As the object is moving and it's horizontal, the friction is horizontal, the friction is constant, the kinetic friction is some constant F of K. And we also learned for an inclined plane of angle theta and having a mass of m, right, that's on the brink of sliding, we found that mu of s is equal to tan theta. So that was a fun video to film. Good luck on AP test and happy studying. I will see you in the next video.